We'd like to invite our last team to the stage, which is iFeather.
Hello, everybody. My name is.
You go.
Hello, everybody. My name is Smalyukh. I am from University of Colorado at Boulder, Department of Physics. I'm here with my PhD student Andrew Hess, and we are very excited and grateful for this opportunity to share with you our technology. If we take an infrared camera and look at the office and home buildings where we live and work, you will realize that a lot of energy is escaping through the windows of these buildings. About 20% of building energy is simply lost through these windows. And we should remember that 80% or so of this energy is actually generated from fossil fuels. This contributes to the carbon dioxide emissions, and just within the US, the energy lost through the windows is equivalent to 70 million tons per year of carbon dioxide emissions. So this is not only increasing the energy demand, but also contributing to the climate change. And the question is there something we could do about this? Well, perhaps we could think about the triple pane, triple silver windows we have in here. Well, unfortunately, they are very expensive, not fully transparent. Their performance is actually not so good, and their durability is limited by steel integrity. Because of this, the deployment is only 5% or even less. And I should remind you that in the US, we still have about 45% or so of single pane windows at the very same time. To truly solve this problem, we would need an insulating material like the aerogels that are used in Mars rover and other space applications. Well, however, you realize that for windows, we also need transparent materials, right? We need to see through them for their primary function. And such materials have not been available until now. Here we introduce transparent, super transparent aerogels that are also flexible and therefore can be simply laminated atop of window panes. You likely did not notice that on this window in here, through which we view the beautiful mountains in Boulder, we actually have an aerogel film. This is because the transparency of our aerogels is much better than that of glass. Glass transmits only 92% or even less of visible light, while our aerogels can transmit 97%. Moreover, by controlling the nanostructure of these materials, we could bring the haze and scattering nearly to zero, and we achieved very high color rendering index, which means that you can view natural colors through these materials without distortions. What's more important is that these materials are also excellent thermal barriers. You can see this by placing a thin 1.5 millimeter thick film on top of a hot plate together with a glass slab. And the temperature of surface of this material, as you can see in here, is very close to the room temperature despite the high temperature of the hot plate at 60 degrees Celsius. These materials insulate equally well also in cold conditions. For example, as we place them on top of a cold surface. And this is because they have very low thermal conductivity of 11 milliwatt per Kelvin per meter. With these materials, we can achieve R5 thermal resistance. And because of their intrinsic low emissivity at the same time, we can now think about windows that will be as thermally insulating as the building walls. Of course, for applications as retrofitting materials, we also need flexibility. And you can see from this video that we can achieve flexibility comparable to that of rubber. And on top of it, these materials can be made water repellent and fire retardant. As you can see, when we place this barbecue fire starter cube on top of our aerogel, it does not burn, right? As you can see. And moreover, as we test durability by exposing them to ultraviolet radiation, by soaking them and baking them, we do not see much of change of their properties, under 1%, comparable to the error of these measurements. Now, what's more is that these materials are made using waste with the help of bacteria. So my students sometimes go to Boulder breweries and take buckets of beer wort like this, not only for free, but even they are offered free cases of beer for taking it. This is waste, right? And they feed this stuff to bacteria, which then, in the process of bacterial biofuel production, make cellulose nanofibers that then can be self-assembled into liquid crystalline colloidal dispersions in large quantities. Then we can convert these self-assembled materials to ordered aerogels through cross-linking, drying, under ambient conditions. And this is very important, that in addition, we can also control the nanostructure and chemical composition so that these materials can be used in many applications depending on the temperatures, transparency, and other requirements of these applications. And so here you can see one of my students holding the dry ice and a fire starter cube on his hand at the same time, right, next to each other on a transparent thin film of aerogel, demonstrating how good thermal barriers they are. This is useful for space applications too, because the temperatures of extraterrestrial bodies can fluctuate from negative hundreds to positive hundreds of degrees Celsius, like in the cases of Mars and Moon, for example. And you can see that we can equally well insulate from such cold temperatures, for example, liquid nitrogen cooled surface in here, using such aerogel films. Now, what's more in it is that these materials are transparent in the visible and near-infrared part of spectrum. So you can harvest solar energy by absorbing it inside of habitats of some kind. And then, because aerogels are so thermally insulating, this energy can be stored like in a thermos. Now, development of these materials would not be possible without a team of undergraduate, PhD, and postdoctoral students whom you see on this picture. My 5-year-old son likes to watch Super Wing cartoon movie. In this movie, there are heroes with special talents and superpowers who always come to rescue. And I feel like this about these students and postdocs whom you see in here. We started from very high-risk idea, funded by ARPA-E. In 2 years, we went from this idea to what I showed you today. Now, we are also collaborating with NASA scientists, and as I'm speaking here today, 2 of our team members, Vlad and Josh, are visiting NASA Glenn Center in Cleveland, because we do believe that there are many opportunities for extraterrestrial applications of our aerogels. Now, within the last 10 days, we had a little baby boom in our team. my postdocs, Chin Kun and Elho, welcomed baby boy and baby girl to their families and to this world. And this makes us think even more about the potential of our technology and the impact it can have, because we do need to save all the energy escaping through the windows so that we can slow down the climate change, so that we can keep the Earth habitable for these newborns, for the ones who will born in future, for the future generations. But this would not be possible if we were not to put this technology on a solid business foundation. And in this regard, a special role is played by my PhD student and my hero, Andrew, who will now discuss the business component with you next. Please.
Thanks, Ivan, and hello, everyone. Let's get right down to the pilot commercialization approach. So we wish to license our product out to insulating glass manufacturers, and because we have gotten $1.8 million in ARPA-E funding to explore the initial transparent aerogel concept, we have been able over the last 2 years, as Ivan mentioned, to actually prove this concept and while de-risking it. And over the next year, we plan to continue this de-risking and scale. So far, we've already made a meter-squared prototype of gel, and we hope to complete licensing by mid-2020 with production and distribution by our IGU licensee to soon follow. We expect that their customers will be municipalities, universities, schools, and hospitals, plus others interested in saving energy. This entire pilot scale approach is supported by our robust intellectual property portfolio, which includes 2 US patent applications and 3 provisionals in the works. So our pilot investor return for our IGU is shown here, where these data were obtained from a very serious conversation with a potential IGU licensee. The summary of this is over the first 5 years, we expect a $54 million return with a 9 times return on investment for our IGU licensee. But there are also other consumer benefits as well, which includes per household a relative savings over conventional double pane window technology of up to $1,000 with a halving of the simple payback period, again for a conventional window, double pane window technology, where the consumer would enjoy a return on investment of up to 5 times. But there are other ancillary benefits as well. Have you ever had a noisy neighbor at night making noise and you couldn't sleep? Well, our sound deadening properties will be able to ensure that you get a restful night's sleep. Additionally, it's worth pointing out that our retrofitting product has these benefits and more, with the added benefit of having super easy, simple peel and stick roll-on installation with 0 out-of-pocket costs, which a toddler could install. So how do we expand to other markets beyond our pilot production market? This plot that I show here is for our transparent aerogel product, and it has been scaled around our initial pilot production. And we clearly see an economies of scaling, and this informs us as we move on to expand to other markets. So, of course, first we're going to enter the IGU market through licensing, and we're going to leverage our royalties to enter relatively high price point, low production volume markets, such as insulation for astronauts and firemen. Plus, and then we can de-risk and scale as we move up in production volume to greenhouses and then our roll-on retrofitting product. This retrofitting product market with the IGUs is actually a $1 trillion potential because of all the pre-existing inefficient windows that exist in the world today. Beyond that, we also want to continue to scale to the building and extraterrestrial insulation markets. And then finally, the general apparel markets, where we show a glove made from our transparent aerogel product. And we can see that, we can only see it in the infrared, where we actually see it works better at insulating the hand than a conventional glove does. And the little girl who's modeling it can see her pink nail polish through it too. So how do we make these dreams come true? First, we need to expand our partnerships with NASA and ARPA-E and continue our market de-risking and research. We also need additional capital financing, investments, and donations to expand to these additional markets. Finally, in order to tackle the scale of the problem, for example, the total area of windows in the world is equal to the area of Indiana, and the total amount of energy being wasted is equal to 2 million going out through all these windows every 15 minutes. We need very large-scale manufacturer and distributor partners. So because of this, we are inspired for transparent aerogels to be on every window in Earth, but also we see huge potential in space because of our of space mining, which could form the first trillion-dollar marketplace, and our technology could enable it. So we firmly believe that the sky is not the limit. Thank you so much for your attention. Yvonne and I will now answer your questions.
How resilient is your aerogel?
Resilient?
Resilient. I mean, if I scratch, does it fall apart? If I handle it, is it going to break?
Yeah, so you could see we could flex those things, right? So not really conventional aerogels that we know can be very brittle, right? If you were to make a window from a conventional aerogel, you would sneeze and it would shatter, right? In this case, the materials are much more robust. The reason is that in the window product, we have cellulose nanofibers that make them not only flexible, but much more mechanically robust too.
So have you tried using your aerogel in a refrigerator to see what it does for?
Not in refrigerator, but we put those on all kinds of cold and hot surfaces. But I think that's another potential that you're mentioning here, because yes, we could perhaps use them for insulation of refrigerators as well. That's also a market.
What's the sound deadening? You didn't give you said it is effective, but you didn't give a measure of how effective.
Yeah, so we are in process of characterizing it, and there was a prior research, actually very interestingly related to NASA's commercialization of space-related technologies. So we read several articles about it and got inspired about opening this yet another opportunity for marketing our product, not just as an energy-efficient film, but also soundproofing material. And so there are these studies in the literature, but we have not yet fully characterized those properties for other materials. We are in process of doing that.
So you said it was hydrophobic. How easy is it to clean?
Originally when we produced the first aerogels, in our laboratory, we worried a lot about the hydrophobicity because the main component originally was nanocellulose, right? And that, you would suspect could be hydrophilic. But we could do chemical modification that made them super hydrophobic. So the contact angle, as you could see from these, pictures that I was showing, is very large. So what this is assuring us about is that such materials will not be somehow compromised during their use, but as a window retrofitting product, we envisage that they still will be laminated between plastic thin films, right? So you would then have a way of unrolling and laminating on top of the interior of a window. So when it comes to the new installed units that Andrew was also discussing, in this case, the aerogel material would be between the glass panes, right? And so, of course, you will have much better thermal insulation in here because of very low, better than air by a factor of 3 thermal conductivity, lower thermal conductivity than that of air. But in addition, you do not need very large gap between the two panes, right? So you can have only 3-5 millimeters or so gap between the panes. So the double pane windows with our gels can be that way much thinner. In this case, however, we do not need to worry about any sort of scratching or whatever, because they are between the glass panes.
How long does it take to manufacture? How fast can you make the cellulose, and how long did it take to make that meter-sized?
So, yeah, it's a very good question. We kind of converted our laboratory to a little factory at this point. You could see that we had square meter gels, right? And we have big jars of these liquid crystalline dispersions. So we actually estimated that in terms of the liquid crystal colloidal dispersion volumes that we are probably beating Samsung and LG Electronics, because our bacteria work so fast, compared to chemists. They can do this job very, very well. So it is really easy to scale, because we do not need 100 clean room facility to make anything of this, right? We rely on nature. There are 10 to the power 30 bacteria on Earth. And we found those types of bacteria who can do just the job we need, right? So we take advantage of their natural processes, and with that, we can scale this quickly, right? We can envisage how such materials could be useful in not just conventional window applications. You could think about a concept of disposable window, right? That you could put as a filter, right? Because air still, although slowly, can go through it and can be cleaned from dust particles, right? So I can envisage a huge market for something like this in cities of China, for example, where you have a lot of pollution and you cannot open window at all, right? Those materials can be thermally super insulating, but yet transparent, very inexpensive, and you could still have the benefit of open window breezing through, right, in some of these applications. Of course, if it will be in Beijing, you will have to dispose your window every week or two, right? But if it's so inexpensive, then it is possible. It is something that we can enable sometime in future.
What would be the...
Have you tested how well it responds to radiation environments?
So we had 500 watt UV bulbs, exposing it over 1 week or so, right? And as I mentioned, we cannot see change of properties that is measurable pretty much, right?
I think she means space radiation,
Yeah.
like
Space
heavy
radiation.
ions.
Yes. So that's a very good question. We have not yet, but as I mentioned, one of the exciting opportunities that I see is bringing these materials to the space where NASA needs them as well, because this is one of the reasons we are in very active discussions and collaboration with scientists at NASA Glenn Center in Cleveland. So we need to learn more what are the conditions under which we need to test, and of course we appreciate and understand that the durability requirements are more stringent when it comes to space applications. One thing I should mention is that NASA used aerogels also for micrometeorite capturing, right? So, they have been used more different kinds of aerogels, not transparent ones we have, right? But, there is a good history there. And we are talking to people who have been developing this technology for NASA applications for decades. In fact, NASA, over decades, is a leading innovator in the development of aerogels. It's kind of very synergistic with the ideas of the entire NASA iTech program, because these aerogels found applications here on Earth already. For example, you might know about a company, Aspen Aerogels, that is producing materials that can insulate pipes. Those materials were commercialized after the NASA developments of aerogels, I believe through some SBIRs or STTRs kind of programs. So we are very excited about this space of opportunities.
What do you think would be the feedstock at production scale? I mean, there's only so much beer in Boulder, for example.
Oh, that's a good question. You see, it can be food waste, right? And there are many other things you could feed to bacteria.
Does it have to be well controlled and consistent, or is it truly wide open in terms of the quality and the taste?
It's a very good question. Yes, so it works well with beer wort. We need to explore other things if we want to have kind of distributed production or centralized production. There are a lot of things that come to mind we need to think about when we will be scaling to trillions of square feet, right, to cover area of Indiana. But the good thing is we are not really restricted to beer wort, right? There would be more research needed to, test how much yield you have under these different conditions and so on. But I think it's all doable. You saw we had a group of superheroes who can test. If you have some other source material you would like us to try, we can easily do it.
Thank you.
You're going to have to definitely look at environmental survivability over time, right? I mean, that's going to be thermal vacuum, thermal cycling with UV light,
absolutely.
like
And
that.
yeah, thank you for this question, because with time constraints, this aspect we did not have a chance to highlight in such details, but we are very close to NREL in Boulder, Colorado, right? And they have this fascinating user facility that is precisely developed for this purpose. And many people from US are using this facility to test different kinds of windows. We are talking to them. We know them very well. This is in plans that we will be testing these windows under all very stringent conditions, and the facility is there for us. In addition, we have NIST Boulder, also in Boulder, right? And they also have a program within NIST that's focused on the on the building efficiency. And they actually have an entire house, right, that they control to make kind of zero energy consumption, right? And with them, we are also in discussions, and again, we are hoping that with our aerogels, with partnerships through ARPA-E, NREL, NIST, and NASA as well, we can do all of those great things.
So one application that really strikes me for you to consider is in cars.
Mm-hmm.
I can have my air conditioner blasting, and if the sun's coming through the windows in a certain way, there's just no comfort, right? And then I lived in Arizona for a while, and you needed oven mitts to touch the steering wheel when it had been parked out in the sun for us. So I think that might be a market as well to reduce a lot of the heat coming into a vehicle.
Yeah, absolutely. And that's something we should discuss perhaps
Yes.
with Andrew, because he showed you this ambitious graph, right, where we'll go to small and large markets and all of this. And I think that car industry indeed holds a great potential, because we could sell for a bit more, right? And so maybe start from lower volume production. So
Right.
yeah, we should.
Sunroofs, moonroofs, all the.
That was free.
That's yeah.
That was free.
That's right.
Can you talk?
Her
Right.
commission,
I just want 0.25% of all your profits.
One quick question. How much money are you raising, and where does it get
Currently we have funding from ARPA-E, right? But Andrew was pitching for investments, donations, and so on, because we don't want to stop here. We want to bring this technology to every window and to the space applications as well.
How much money and where does it get you?
So we're confident that our initial 1.8 million will allow us to reach a scale and a de-risked level that it will be attractive to licensees. So we do not intend to, at least for our pilot market, to sell and make it, right? We're going to license out the intellectual property. That's the key aspect.
So have you done some pricing analysis on that at all?
We have, yes.
Okay, can you talk to me about that a little bit? I don't know what your costs are here, and so I don't know if you're selling into that initial low-end market.
Right.
Are you talking about a 50% increase in cost of a double pane window? What are you talking about here?
Right, yeah, no. So actually, $4 increase with, a nice margin. And actually, as the gentleman from VTech explained, the glass materials on the inside of the window is only a small fraction of the total window cost, because the frame and installation makes up a very large portion. So we're still really safe. We'd only have a very small premium for introducing this, even at a low pilot production volume, into the window market.
$4 per unit, $4
Per
per
do-
square foot?
Per square foot, yeah.
Okay. Hey guys, I got to cut us off
Okay.
and encourage you to continue the conversation at the impact tables this afternoon.